Okay, so the go live thing was an absolute fail. We're going to do a video for the product rule just using the old uploaded video. So first off, the product rule helps us when we have a function f of x that is a product of two other functions, f of x and g of x. And so a few things need to be true. Both of these functions need to be differentiable, which means they need to be continuous at the point of interest that you're looking for the derivative of. And then essentially we can go ahead and calculate a derivative of a product using the rule that the derivative of our product function is going to be the derivative of the first function multiplied by the second function plus the derivative of the second function multiplied by the first function. And so that rule would be what we would use to take the derivative of any function that was just a product of two different components. So this expands our ability to take derivatives then, and we'll take a look at a couple of examples before we get into the actual proof. So just remember it's the derivative of the first times the second plus the derivative of the second times the first. And that'll be quite useful to you in your differential equations classes in second year as well. So let's take a look at an example. We'll start with a function that's a product of two functions. Suppose we start with, well, let's go with sine x, cosine x. Now I know some of you would be screaming to use the half angle identity to change it to a single function and use the chain rule, and that could absolutely work. Sorry, the double angle identity. But instead we're going to use the product rule. So to take the derivative, I have to take the derivative of each component. So the derivative of sine is cosine. So I'll have cosine x times cosine x because I multiply the derivative of the first times the second. And then I'll multiply the derivative of the second times the first. So the derivative of cosine is negative sine. And multiplying by the first function is sine x. Now remember, it's the sum of those two things. And this one we could simplify a little bit further. So this is cosine squared x minus sine squared x. And if you remember your identities, this is an identity. In fact, it is the cosine of 2x. This would be enough information though right here, and even this would be enough information to help you calculate the slope of a tangent at any point. So if you wanted to know the slope of a tangent to f at a point of pi by 4, you can just substitute pi by 4 into each of the places where x shows up, or into here, or equivalently into there. Sometimes trigonometric identities are particularly useful because they help you to simplify a little bit further. So there's an example. Let's go and do another example, and perhaps this time with something that's a polynomial. So let's take a look at 3x cubed plus 2x times x to the power 4 minus 1. Now, I know we could just expand this polynomial out and then gather our terms, put them in standard form, and use the product or sort of power rule for differentiation to do this term by term. But why not go ahead and use the product rule and see if it makes it any easier for us. So we'll take the derivative of the first component. I'm going to leave that in brackets because it is two terms. So the derivative of 3x cubed is 9x squared. The derivative of 2x is 2. And I'll multiply that by the second component, so I'm not changing it at all. Then I'm going to add to it, and I don't have enough room beside on my camera. I'll move it during the next scene. But I'll add to it the derivative of the second portion. And again, I'll put it in brackets. So this will be 4x to the power 3 minus, well, the derivative of 1 is 0, so I suppose just 4x to the power 3, multiplied by 3x cubed plus 2x. So again, it's the derivative of the first times the second term, and the derivative of the second times the first term. And that's how we go ahead and use the product rule. Once you've got the derivatives, you can calculate slopes of tangents, slopes of normals. You can find the zeros of the derivative to go ahead and find your critical points. But all of the stuff that we learned from differentiation originally is just going to hold in the exact same way. We just now have another rule to tackle slightly more complicated functions. And this actually saved us a fair amount of time if we think about expanding and collecting like terms. Where this gets even more useful is when we have perhaps an example like that, where we have a product rule that also contains maybe a chain rule function. So there are two functions here. We have this first function and we have this second function to the exponent 4. But the second one, when we find its derivative, we're going to need to use the chain rule. So the first part about using the product rule to find the derivative of f of x is easy. It's the derivative of the first times the second. Well, that's just 1 times x plus 2 to the power 4. The second part is the derivative of the second, which will be slightly more complicated because it's a chain rule derivative. So it'll be the derivative of the outside, 4x plus 2 to the power 3, times the derivative of the inside. Well, nicely enough, the derivative of x is just 1. And now that we know the derivative of this term, we can multiply it by our original first term to finish off the product rule, because it's the derivative of the first function times the second function plus the derivative of the second function times the first function. And so that's the chain rule. You could simplify here. I think we could factor out x plus 2 to the power 3 from both terms, and that's something that we would commonly see. And then that leaves me with, well, there's 1x plus 2 remaining from the first term, and then there's 4 times x plus 1 remaining from the second term. And you could continue on and simplify. I'll just simplify one more step here, just because I really don't like that set of brackets being so ugly. So we have x plus 4x, or 5x, and we have 2 plus 4, or 6. So the derivative of this turns out to be this. You can imagine expanding x plus 2 to the power 4 would be time consuming. Even if you use the binomial expansion, you then would have to multiply each term of that binomial expansion by x plus 1. So this would get pretty long. If you're wondering what happened again from this step to this step, we saw that the x plus 2 was common to both terms. So we had 4 of them here and 3 of them here, so we common factored out 3 of them here. And so that's basically using the product rule. Now let's go ahead and prove it. So I'm going to have to clear some space. And I may need some more colors, so I'll just collect my chalk. So we'll start off by defining our larger function. F of x is equal to f of x times g of x, as we saw in our rule. And if you just back up the video, you'll see what it was that we had to prove. So to find the derivative of f of x, well, I mean, I know the rule, I could go ahead and use it, but I want to prove the rule. So I'm going to go right back to first principles. And so that's the derivative of, the limit of f at x plus h minus the limit, or minus f of x, all over h. And that says h approaches 0. Now this is capital F, so this x plus h needs to be substituted into each of these terms. So this will now be the limit as h approaches 0. And I'm going to adopt some colors here. So this will be f at x plus h times g of x plus h minus f at x times g of x. And I hope you can see the colors okay on the video. I think you can. So we've just gone ahead and substituted x plus h into there for the first term and x into there for the second term. Well, I think I'm probably going to have to split up this limit somehow. But unfortunately, I don't see a way. And this is where sometimes creativity, like the creativity you need to complete the square, can be involved. In completing the square, we learned to find the vertex of a parabola by adding and subtracting something so that it would work out the way that we wanted it to. Well, we're going to do a very similar thing here. We're simply going to add and subtract a couple of terms to my numerator. I think I'm going to add this term. What am I going to do? Yeah, we'll go f of x times g of x plus h. So if I've added it, I also have to subtract it. So minus f of x times g of x plus h. And it's at this point in the proof where I try to remember if I was supposed to add f of x plus h times g of x minus f of x plus h times g of x. But I really can't recall. I think the only thing that will be different is the signs will perhaps change. Well, now I'm going to group these. So I see that I've got f of x plus h right here multiplied by g of x plus h. I also have a negative f of x times g of x plus h. So I'm going to put those two terms together. Then I'm going to put these other two terms together. But I am going to change the order of the pink ones. I'm going to write this one in front of this one. So my next line is going to have the same four terms, but I'm going to put the two orange ones together, and I'm going to put the two pink ones together. So this will be the limit as h approaches 0, and we'll start with the orange. So it's f of x plus h. I'm going to keep my green, g of x plus h. Now I'm going to subtract f of x, but that's multiplied by g of x plus h. Then my pink terms. So I'm going to have plus f of x, which I've got multiple colors of chalk, and I'm going to do this term first. So times g of x plus h. And you might be wondering why I've switched from green to white, but that'll be clear in a second. And then I'll subtract f of x plus h, f of x times g of x. And remember, that's still all over h. Now, my rationale for writing my g of x plus h is in green and my f of x's in orange is simply because of the fact that, well, I wanted to try to common factor somehow. So you can see that I have a g of x plus h common to both of these terms, and I have an f of x common to both of these terms. So I'm going to common factor these, but I'm also going to do something else. I'm going to decompose this fraction. So I'm going to write this as the limit of this first term plus the limit of this second term. And that will allow me to take into account properties of limits, which will let me distribute this limit over the first term and the second term separately. Now, unfortunately, well, do I carry the laptop over? All right. This may be a technical fail, but we're going to try. Oh, I think it's going to work. How's that? I think we are in some more space. If you need to see what we had before, you can just back up your video slightly. But my next term is going to be the limit as h approaches 0, and I'll distribute that limit in now. And I'm also going to common factor my g of x plus h to the front. So then I'll have f of x plus h minus f of x over h. So that was the entire first term. And I'm distributing that limit through. I'm also going to remove the subtraction sign, or sort of the addition sign. And now I'll come factor my f of x out. So that was f of x times g of x plus h minus g of x. Now, if you happen to be thinking about your properties of limits, you can probably work fairly quickly through this. This is the limit of a product, so I'll be able to create this as the product of the limits. And I'll do that to both terms. So that's distributing through the first term. And then now I'll have to distribute through the second term. And now I've just used another property of limits, the product rule. So those properties of limits we discussed earlier certainly came back to help. Now, this first limit is not indeterminate. So I can substitute in a value of h equals 0 wherever I see an h. And I see an h there. So when I evaluate that first limit, well, it's simply going to be the limit as h approaches 0 of g of x. So it'll be g of x. Now, the second limit we should recognize. The second limit is the first principle's derivative of f of x. Right? It's just simply f of x plus h minus f of x. So this will be f prime of x. Likewise, when we substitute h equals 0 into our that second limit's also indeterminate. The limit of a constant is a constant itself. I know f of x isn't a constant, but with respect to h, it absolutely is. So this will just be f of x. Get rid of that green. And this second limit, well, I believe that's just the first definition's principle of the derivative of g of x. So this should just be g prime of x. So I'll have f of x times g prime of x. Now that's not exactly our product rule that we started with, but addition has this wonderful property of being commutative. So I can just take this term and move it to the front. Of course, it doesn't really matter. If when I do the product rule, I wanted to do the second function times the derivative of the first plus the first function times the derivative of the second, I could, and it would be equivalent. But just for sake of, I guess, showing off, we're going to rearrange so that we get exactly what we were setting out to find. And that is that it's the derivative of the, oh wait. This is the part in the class where I make a mistake, and normally Thomas would be around to correct me. I already had the derivative of the first times the second plus the derivative of the second times the first. I just didn't have them in the right multiplication commutative order. But fortunately, 2 times 1 is the same as 1 times 2. So I suppose I should get rid of that showing off now. It seems a tad ironic. And instead, I'll just write this out as the derivative of f of x times g of x plus the derivative of g of x times f of x. And that's what we were required to show.